Signal, WhatsApp, iMessage, FaceTime, Discord, Snapchat, Zoom, Microsoft Teams, Google Meet, OneDrive, Proton Mail, and many, many more. All of these share one in common. All of them are encrypting your data end-to-end. Today we're going to look at the RSA algorithm that can be used to encrypt the data from end-to-end. So I want you to imagine the following scenario. Alice and Bob want to send a message between them, but they don't want the public to know about it. Usually no one is supposed to know about it, but if someone catches the signal, they could read a clear message. That's why we have to encrypt our data. In the beginning, first of all, if we use technology, computers only understand numbers. So we already have to encode our message into numbers. Therefore, each letter becomes a number. For example, in the ASCII encoding, every character maps to a unique number. In our example, H equals 72, A equals 65, L equals 76, and O equals 79. So to transmit the message hello, we already have to encode it into the number order 72, 65, 76, 76, and 79. This is already harder to read for just the normal person, unless they know that we encode it in the ASCII code. The RSA algorithm works with two keys, a public key that anyone can use to encrypt the data, and a private key that only the owner of the private key can use to actually decrypt or read the final message. First, we need to pick two large prime numbers. In this example, we're going to take P, 61, and Q as 53. It's important that they are not the same, and the larger we make them, the harder it gets for everyone else to decode our message without the proper keys. If we multiply 61 by 53, we get 3233. After we multiply it out to prime numbers, we need to generate our keys that can be used to encrypt and decrypt. Therefore, we need to first calculate the totient. That's a phi of a variable. And phi of n in our example is 3233, is the equivalent to p minus 1 times q minus 1. And remember, we got n through p times q, and phi von n we get from p minus 1 times q minus 1. So first, to get the public key, we select a random exponent e that is bigger than 1 but smaller than phi from n. And it's important that e does not share a common factor with phi. They have to be coprime. So how do we generate the RSA keys? First, we need to calculate the totient. We receive the totient from n through multiplying p minus 1 times q minus 1. After that, we choose a public exponent. The exponent has to be bigger than 1 but smaller than the totient from n, and the e is not allowed to share a common factor with the totient from n. They have to be coprime, which basically means that the only factor they share is 1. So for example, 3 and 5 only share 1 as a common factor, so they are coprime. After we found our exponent e, we need to get our exponent d. To find d, we need to find a number that d times e equals 1 modulo of phi von n. Sounds complicated, but in an example you will see it's pretty simple, actually. So this d is the unique private key that's only known to the receiver of our message. Now that we have all of this, we can say our public key is the pair e and n, and the private key is d and n. So if we go back to our example of sending the message hello, we first calculate n. N is p times q, which we chose 61 and 53, since they are coprime to each other. This is the equivalent to 3233. After that, we calculate phi von n. Phi von n is p minus 1 times q minus 1, which in our example would be 60 times 52, which is equivalent to 3120. After that, we choose the public exponent e. In this case, we can just simply take 17. Why 17? Because it's coprime to 3120. After that, we need to derive the private exponent d. To find d, we need to find a number that's multiplied by 17 is the equivalent to 1 mod 3120. You can find this number by calculating 1 plus 3120 times x. And this number needs to be divided by 17 and land on a flat number. In our case, x would be 15, so 1 plus 3120 times 15 would be around 218,801. That divided by 17 would be 2,753. This is how we get our private key, 2,753 and 3,233. So now that we have our keys formed, the public key 17,3233 is the one that Alice uses to send her message to Bob, and Bob decrypts this message using his private key 2,753, 3,233. So if Alice now wants to encrypt her message, in this example, she first wants to encrypt the first letter, which is H, the equivalent of 72, using the public key 3233. She needs to fill the formula C equals M, the message, to the power of E, mod n. So C, the encrypted message, would be 72 to the power of 17, mod 3233. As you can imagine, 72 to the power of 17 is quite a large number. This is especially where this gets complicated if you don't have technology to make these calculations for you. But you can just put it into the calculator, since this number, at least in my case, is bigger than the maximum value that my calculator can display. So you need to calculate it step by step. But at the end, you will receive 3000. So the letter H that we wanted to encrypt becomes 3000. And this is where now everyone receiving 3000 sees the number 3000 and just doesn't know what it means, how it's encrypted, how they can read it. So Bob receives this C that is 3000, and even he couldn't just read it, he has to decrypt it now. Therefore, he uses his private key, dn, which is equivalent to 2753 and 3233, to recover m. And m is the equivalent of c to the power of d mod n. As you can see, here the numbers are way bigger, so the calculations is even more calculation heavy than the encryption part, but this is just due to the numbers that we chose. So if m is the equivalent of 3000 to the power of 2753 modulo 3233, we end up with 72. So he assumes the original message was 72. If he looks in the ASCII table, 72 is equivalent to H. So if none of both parties made a mistake through encrypting or decrypting, they end up with the same message. So this process ensures that only Bob with his unique private key can read Alice's message. If we now go back to the original plan of sending the full plain text hello, encrypted through the system we just went over, we received the 5 numbers that represent the message: 3000, 2790, 2726, 2726, and 1307. These 5 numbers are what's floating through the internet. That's what everyone receives that tries to catch our data on its way. And then when Bob receives receives these 5 numbers, he can decrypt it to end up with the same plain text that we sent. That's the concept of the encryption that gets transmitted and then decrypted. So our data stays safe while being transferred through the internet. But now, the RSA algorithm is an algorithm that just takes the number that we choose and starts to calculate with this. We took the ASCII value of age, which is 72. But if we go ahead as Alice and Bob, before we write our algorithm for our specific case, we can decide, well, age is going to be the number 8, not 72. Of course, we have to do this for every single symbol that we want to use, but this ensures that it's individual for everyone. And this is also what messengers use for your specific encryption in your chat. Not every chat has the same encryption model. Every chat has a different code that they use to calculate messages. So why is the RSA actually so secure? As we have already seen in our example, first, multiplying 61 times 53 is equivalent to 3233 was pretty instant. But for everyone who doesn't have these prime numbers that we, of course, are not allowed to share if we want to keep it secret, everyone just knows about 3233. But no one knows how we actually got to 3233. Since they are not just 2 plain values that end up equaling this number, we can use any amount of numbers. And modern keys that want to be secure take numbers in the range of 2048 bits or more, and this is such a high number that brute forcing it, so just going through every single possibility, just simply would take billions of years, and we don't have billions of years to just decode one message. Additionally, another security point we can make is changing these numbers every 24 or 48 hours. This way, even when they had the original amount, they have to make it now in our time limit. But now that the future of quantum computing is coming a bit closer, the time decreases drastically since quantum computing scales exponentially. But therefore, our bit count is just simply increased because this also scales exponentially, and therefore you can just work against it, partially at least, for the time being. So you could say RSA powers the modern internet. Of course, it's not just the RSA algorithm, there are multiple of these algorithms, but this was an example that I wanted to make. It's used to secure websites through the HTTPS. We use it for digital signatures to make them individual for each signature. We use it to encrypt our message. We use it to encrypt our passwords and usernames. And this way try to keep all our data going through the internet that's already public out there, at least slightly safe. But now coming closer to the end, it was quite a lot. So I want to go with a simpler example over everything again, just to summarize. This is the part that you can watch multiple times if you ever need. Its design's pretty simple, and just to summarize everything that we did. So how do we encrypt? First, we choose 2 distinct prime numbers. Let them be P11 and Q3. They have to be coprime, which means they are not dividable through each other. Then we need to calculate n. N is the result of P times Q. This is a part of the public key. After that, we calculate the totient von n, so phi von n, that's P minus 1 times Q minus 1. In our example, 10 times 2, which is 20. Now we find a public exponent e, that's coprime to 20. We can choose 7. After that, we calculate our private exponent d. So we have to find a number where d times e to the modulo of phi von n is equivalent to 1, or d times e is equivalent to 1 modulo phi von n. Doesn't matter how you put it, you can just enter your variables and use a calculator to calculate it. In our case, d is 3, so we have our public key 33.7 and our private key 33.3. So as an example, we are going to encode OK. In our case, we chose for O to be 15 and for K to be 11. C, our encrypted message, would be 15 to the power of 7 modulo 33. 15 to the power of 7 is 170,859,375. And this modulo 3 equals 27. How do you get this number? Again, this is, you take the big number, subtract 33 so many times until you can't subtract it anymore unless you want to go into the negative area, and that's your number. In our case, 27. 27 is the encoded message that we would send for O. After that, we want to encode K, where we chose 11. So our encoding for 11 would be 11 to the power of 7 mod 33. 11 to the power of 7 equals 19,487,171. Modulo 33 of that would be 0. Why this is problematic, we are going to cover in a second here. So the original message, OK, is the values 15 and 11, and the encrypted message is the value is 27.0. 27.0 is what gets transmitted through the internet and ends up at our receiver, in our case Bob. Now that we are at the endpoint, we want to decode our message and optimally get OK back. So using the private key 33.3, we can decode 27. 27 to the power of 3 mod 33 is 19,683 mod 33, which is 15. As we have decided, 15 is O. This worked perfectly fine. But now we have to decode 0. 0 to the power of 3 mod 33. 0 to the power of 3 is still 0, so 0 mod 33 equals 0. This is where our problem occurs. The encrypted message was 27.0, the decoded message was 15.0. So we just got the O back translated, but the K went missing through the process. This is problematic in decoding and often avoided because the message just can't be translated backwards. This is where we need to find a different value for K that's not 11, because 11 would end up with the 0 and the loss of the data, which is why you always want to avoid having in the encrypted message or the decoded message a 0, except if you decided that 0 would be a specific value. But usually, due to it just simply being a source of mistakes, you try to avoid it.